Question 3, ideal step-down transformer, primary to secondary ratio of 6:1. Input power at the primary is 40 watts, so P is 40 watts. Input voltage is AC, RMS value of 240, so V equals 240 volts, so that means that I equals P over V, because remember, P equals VI. So that gives us 40 over 240, which is equal to 1/6. Now, normally I wouldn't write that as a fraction. It comes out as 0.17 as a fraction, as a decimal, 0.17. But I happen to know, because I've done a few of these questions, that if it's a step down, so it steps down, so V steps down by 6 times, so current steps up by 6 times, which means that 1/6 times by 6 equals 1 amp, which is here. But we could also do this by saying V primary over V secondary equals I secondary over I primary. So therefore voltage in the primary was 240. Voltage in the secondary, because if we go step that down by 6:1, step down, that means then that our voltage goes from 240 divided by 6, which is equal to 40. So that's 240 over 40 equals I secondary. We don't know. Over I in the primary, we said was 0.17. So I in the secondary, 1 amp. So that's why it's that one. Righto, graph below shows the variation in magnetic flux. So variation in magnetic flux of a coil as a function of time. Which one of the following graphs best represents the induced EMF in a coil? Okay, a bit of a typo there. So one thing to think of here is when we talk about changing magnetic flux, we're actually talking about the gradient. Now, we know the gradient at the turning points is 0. Okay, maximum gradients are here and here. So that means that maximum gradient is going to give us a maximum flux up there. That's a positive gradient, so it should actually be from down here, because remember we've got the EMF equals negative N change in flux over change in time. So that's Faraday's law. That N is due to Lenz's law. So it's going to look like a cos graph, which means it will look something like that one.